Hello, everybody. Welcome back. Happy Wednesday. This is again another section of Bed Talks. I hope you're doing well. So kind of going forward now, we are in Calculus 3. So kind of thinking about the story of Calculus 3, and we're ending with this chapter. And why this chapter? Why do we actually get to this? So let's think about the story of Calculus 3. So what do we start off with, right? Our goal in Calculus 2 was basically take our sections calculuses 1 and 2, and bring them in to 3 dimensions and multiple dimensions so we can utilize their techniques in different dimensions. And we saw that most of the time we're able to do exactly what we think we should be able to do, right? We were able to integrate in the same way that we want. Right? We were able to take derivatives in a very similar way, in kind of making it a little bit more generalized. Being able to write equations of lines and planes and things like that, extending that. And this last chapter here is all about combining a lot of these things that we kind of tackled. So a new concept that we learned in Calc 3 was vectors. Thinking about how we think about direction and magnitude at a certain point, kind of velocity. That's how I'll usually think about vector fields. And then combining calculus with that. So what do we mean by calculus, right? The ideas of using integration, differentiation, and all that. And how can we combine both of them? And these ideas in chapter 16 are actually just an incredibly beautiful way to end calculus. At least this part of calculus here, of trying to be able to combine all these different types of processes and information that we've utilized over the last several weeks in this course. So what I'm going to tackle today are 2 sections, the 16.1 and 16.2. I'm not going to talk too much about vector fields because that's just something that we'll see over and over again. So we're going to get to see a lot of that over the next couple of weeks. But it's going to be important for us, at least here, to get at what actually is a vector field. So we're going to tackle vector fields and also line integrals today, specifically. Over vector fields and just regular line integrals in space. So let's first all talk what a vector field is. Now, vector fields occur every single place in our entire world. We can think about them as wind, or ways that an electric current flows, or kind of how a virus spreads in some way. We're all little vectors and we're moving in those directions. So in this case, what we call a vector field, in most cases, right, we have a function. Right? If I tell you this, I have a function f of x, y, it's equal to x squared plus y squared. What I usually mean by this is every single point, x, y, I give you a point, x, y, and you tell me a z coordinate, right? And then that kind of thinks about a height. But now what if I say instead, I have this vector quantity, and I tell you that I want to, at every single point, define a vector. And this is kind of the idea of a vector field. So at every single point, I am defining specifically a vector. And we could think about that. If I'm at a certain point, where will I be moving in the next direction, right? Where will that direction go? And this idea of a vector field is really, really important. And we can extend this to multiple dimensions. Note a couple of things in my notation here. First thing you should notice, I'm using the vector of this function f. It's a vector function, we call this. We call this a vector function or a vector field. We usually will denote this as a vector field, but this is a type of function, right? It's a function. It has inputs and it's an output. The outputs here is not a number. The output here is a vector itself. So we can also do something like, 2, 3 zy, and then z squared times x, right? This could be a vector field. I plug in a coordinate x, y, z. You tell me a direction I should be going in at that 3-dimensional things. And we can extend vector fields going on forever. But how do we start to draw these things? Right? They're really tough to think about, honestly, if you don't at least start to draw them out. So we're going to draw at least one here to show you how the process of maybe how you would want to go about it. So if I took the vector field f of x, y, let's call this negative y, x. And this is the vector field we will try to tackle. And how do we draw this? So the first thing to note, and the big thing to note in a vector field, is when I'm drawing my vector field, the length of the vector is determined by the magnitude of that vector, specifically. So we need to be plotting these things. We need to be plotting vectors, and we need to be plotting, making sure that we understand the length of the domain. the length of the magnitude of each vector that we plot. So the longer the vector, the faster I will be going in that direction. So you might say to yourself, okay, how do I even start this, right? How do I even start plotting these? How many do I need to plot? There's not really ever a really good answer, but you just want to get at least the gist of it as we go forward, right? You just want to get the gist of it. So what I usually like to do, in my opinion, I usually like to start on the axes to see what's happening on the axis, the x and y axis. So on the x-axis here, we have that y is equal to 0, right? That's what's usually defined there. So if I plug in f at x0, in this case, I'm just going to get 0 comma x. Now, what kind of a vector is this? Right? What kind of a vector is this? Well, let's say I plug in 1. I'm going to be 0, 1, which is directly up. So as a reminder on how do we draw these, we usually start at the point that we are drawing the vector at. So I start at 1, 0, for instance, f of 1, 0 would be 0, comma 1, which is directly up with a length of 1. So let's say like this, here, just like that. I start at that point and I go upwards. We can continue doing this, maybe f at 2, 0, and we note here that as I move down the x-axis here, my length of my vectors, my direction is going to stay the same, but my length is going to increase. Kind of like this. We get a nice gist as we keep going farther down. Now, what happens on the negative x side? Well, if I plug in, for instance, f of negative 2, 0, it's going to be 0, negative 2, which is going to be going actually down, straight down in the y direction. There's no movement in the z direction, right? So we can kind of imagine that as I move down this way, I'm going to get the same exact kind of idea there. Kind of, if I'm over here, I'm going to be moving in this direction. If I'm over in that side, I'm going to be moving in that direction. Now what happens on the y-axis, right? What happens there? For the y-axis, we are again going to have when x is 0, and we can plot this, and we get f of 0y, or phi, is negative y, 0. So think about what this is doing. I am now only moving in the x direction. And this is a really important idea of kind of making sure we relate that a point does not, at every single point, it's going to dictate a direction. So for instance, I only have my y coordinates here, but I could be moving in the x direction. It's kind of a weird thing to think about. Just kind of make sure you're aware of that. So it's kind of thinking about this, right? What's going to happen here? Let's plug in just a point. Let's plug in some positive points. I get negative 1, 0 at point 0, 1. So if I'm here, I'm going to be moving in the negative x direction. And I hope you'd agree that as I increase my y, I'm going to be moving farther and faster and faster in the negative x direction here. So something like this. We can maybe start to see what's going to happen here. So if I'm here, think about what's going to happen. I might start to, travel in this direction, and then maybe come around this way and kind of come about that way. So let's think about a little bit, just do a little bit more here. Let's go in the negative y direction. What if I do that? Maybe I plug in 0, negative 2, for instance. I'm going to get now negative 2, which is 2, 0, which is directly in the x direction. Kind of like this. And as I go farther and farther and farther, might be a little bit too long there. It should be increasing linearly. We get that point. So it almost looks like a rotation field. Now, you might say to yourself, well, what about these areas that I really didn't check out? We can kind of make sure that we at least understand what's happening there. What we could do is maybe the next step, which I would maybe suggest doing, would maybe be the axes, the y equals x and the y equals negative x. Let me just show you what happens at the y equals x here. If I do y equals x, that's when my coordinates are x comma x. So if I plug this in, I'm actually going to get negative x, x. So my plot there, if I give you an x coordinate, it's going to be negative x, x. So if I plug in, for instance, f11, which is this point like around right here, right? I'm going to get negative 1, 1. I'm going to move negative in the negative x direction and the positive y direction. So I'm kind of going up at a 45-degree angle this way. And we kind of see that as I get bigger and bigger here, 2, 2 is going to be negative 2, 2, negative 3, 3. So the magnitude is going to actually increase drastically as we go farther. And you can probably assume then, if I do this and I go the other way, that's going to be the exact opposite way when I go this way. And we start to get our full rotation. If I go this way now, we can go ahead and keep doing this here. But the idea is that this is actually a rotation field. So what is this vector field actually saying? This vector field is saying, if I place a point somewhere, let's place this point right here, where will I travel? Right? You can probably see I'm going to travel in a circle. That's all I'm going to do. I'm just going to travel in a circle at the radius that I'm at. I'm going to be traveling in this direction here. I was kind of just looping around like that. What I've just drawn here, this red line, this is actually called a streamline or a flow line. And they're actually really important because they show us what a trajectory would be like if I just placed a point down and I just kind of went with the flow. Have you ever been like to a water park and you just kind of sit in a tube and you just kind of let it go where the water takes you? And that's kind of what the idea of a streamline is. That's the streamline, right? It's kind of just, what is it doing? And as you probably imagine, as I go farther and farther out, the streamlines will get bigger and bigger circles. These are supposed to be actual circles and not ovular shapes that I'm making. That's the idea of vector fields. We can draw these a lot. Sometimes it might be tough to visualize some things, but that's why you have Mathematica a lot of times, to be able to visualize some of these. So what are some important ideas of vector fields? Well, the first main one of a vector field is that there's some important types. And the important type here is called a conservative vector field. Now, what does a conservative vector field actually say? The conservative vector field, well, harkens back actually to something that we talked about in chapter 14. And so we're going to need to remember that. So take a function f. I'm actually going to define something as I'm going to define it as phi. Okay, this is the letter phi. If I have a function phi of xy, I'm going to call this a potential function. Now, if I take the gradient of this, I hope you'd agree that that would give me fx. Let's assume that's in terms of just x and y. So I take phi x and phi y, phi sub x and phi sub y. I'm just taking the derivatives. That's the gradient, right? The gradient is the derivative with respect to x and the derivative with respect to y. This itself, I hope you'd agree, is a vector. And as you can probably imagine, this could be a vector field. I could actually define this as a vector field f, which is the gradient of a function, which I'll call the potential function. And the gradient here, this function right here, this idea, you know, this vector right here, this vector field is called a conservative vector field. So a conservative vector field in its most basic form is you have a conservative vector field if there is a potential function phi such that the gradient of it is equal to our vector field. Now, for instance, what does this look like? What do I mean by that? So let's say I give you this potential function phi of xy is equal to, you know, 2x squared y squared. Okay. If I want to compute the gradient of phi, this is going to be, the gradient of phi here is going to be, well, the gradient with respect to x is just 4xy squared. The gradient with respect to y is going to be 4x squared y. And this right here, we call this a conservative vector field. Now, you might say to yourself, well, are all vector fields conservative? The answer is no. And how do I know that? Well, we'll be able to find out if I give you a vector field. For instance, if I give you a vector field, is that vector field conservative? There's a lot of different ways to check it. There's a really quick way to check it, as we'll see in a couple of sections. But it's actually just a really important idea when we go forward on the idea of a conservative vector field. So a conservative vector field is the gradient of a potential function. We call that phi a potential function. And that's going to play a really, really big role in a couple of sections here. That's the basic gist of 16.1. That's the main takeaways here. So now when I go to 16.2, and we kind of go forward here, we kind of do a hard shift again. It's kind of a couple, we kind of have to go back to how we kind of talked about in section 12, chapter 12, where we're going back and forth for a couple of concepts, at least off the bat. And then we're going to kind of coalesce them near the end. And that's kind of what's going to happen here. So let me at least start to bring up this idea. So what did we tackle back in chapter 15? We had this integral, this double integral f of xy dA over d. Now, what did this actually mean, right? Well, I have this function f of xy. I have this domain D, right? I have this maybe this interesting domain here. I'm actually going to draw a specific domain. It's going to help me out. Something like this. This is over my domain here. Something like this. And what we saw was, if this is f of xy, this is my domain D down here, this calculated the net volume. Right? What we did is we took f of xy over this domain D down on the xy plane, and we kind of thought of f of xy as a height, right? Kind of thought about that. Now, so this was representing a net volume. So now, one way we might be able to think about this too, and another type of integral we might want to say is, okay, well, what if I just wanted to find this value here over a curve on my xy plane? Now, what do I mean by that? What I mean is, say I had this curve going from here to here. You see the green dots right down here, these green dots. Let's say I take this curve, kind of like that. If I trace this out on the top here, like this, in a certain way, that's kind of just going up, kind of like this, and we actually get something like this curtain here. So what am I doing? I have this curve now. I'm going to delete this domain C here. I'm going to name this curve now D, C, specifically. This curve C, and I'm just calculating the function value at every single point on this curve C. I'm calculating f of xy on that curve C. And what's interesting here is I can actually start to piece those together. We get this kind of fence aspect, this curtain. And this curtain is, I hope you'd agree, an area, right? Because it's kind of a length times height, and kind of a length times height here, length times width in some way. So it's kind of this flat object. And so because of that, we can actually start to calculate this if I wanted to. And that's what the idea of a line integral is. And so the line integral, so a line integral here is, we define this as a single integral over a curve C of f of xy ds. Now, I want to mention a couple things here. This is what this interpretation is. That this interpretation is a net area, actually. This again could be negative because I could be below the xy plane here. And again, I can kind of think about it in this way, right? If f of xy was negative over my domain D, right, this could be negative too. So I have to think about this as a net area. Think about how much this is above and below. Because we're now getting back to something like a Calc 1, but now I'm thinking about a line that could be anywhere in space, which has become a pretty interesting problem. Now, with this, you might say to yourself, okay, what's this ds here? What's that doing? Well, that's arc length, right? This is saying with respect to arc length. This is with respect to arc length. And if you remember back when we were doing chapter 13 here, we saw that arc length was really interesting and had some really important things, but to evaluate an integral, to evaluate things with, to take derivatives with, it's horrifying, horrifyingly bad. So how do I actually evaluate something like this? So for instance, if I told you now, like let's say I had a problem. Let's say I had this. Let me give you a problem and we'll come up with an idea of how to solve it together. So here's the problem. Here's the question. The question here is, if I give you the integral over C of xy ds, where C is the right half of the circle of circle x squared plus y squared equals 16. And this is my problem that I'm trying to solve. How would I even go about doing that? So the problem used to be, right, if I had over a domain, right, I would think about in terms of x and in terms of y, right, I would write a type 1 or type 2, maybe I would go something like that. But here I have a curve. I don't have a bounded domain, I don't have anything. So how do I go about this? Especially this ds is a problem. So if you recall, one thing we like to do was actually shift this to a time integral, because we have a nice representation between, arc length and time. We actually did this back in the day when we tried to compute some arc length in this case. So this is a reminder. I'm going to write this down here. As a reminder, we had that s was equal to, a to t. We had this parametrization of our curve c, which we denoted as r. And this r of t here is r of u in this case. We took the magnitude of the derivative of that. That's what we did. So we found that this arc length was actually equal to the integral from a to t of the magnitude of the arc length, or magnitude of this velocity vector. And what we could do is, kind of working with this, we use the fundamental theorem of calculus to take the derivative of both sides. When I take the derivative of both sides with respect to t, using the fundamental theorem of calculus, I plug this t into here. And I would get something like r prime of t, the magnitude of that. So what we can do then is I cross multiply. I can tell you that ds would have to be equal to magnitude of r prime of t dt. And so this gives us a key in order to change this integral right here into something that I might be able to integrate with respect to time, because I know how to parameterize curves. We know how to parameterize a curve C, especially if I have a line segment, if I'm on a circle, if I'm on really any domain. If I have the function value, we can come up with parameterizations all day. And so because of that, we can come up with possibly a parameterization for this. And so how do I now evaluate this thing right here with respect to this arc length, with respect to arc length? I can't. I have to do it with time. We like things in time, and it makes a little more sense. So what we need to do instead is we take this, we replace this with ds, and now what I'm going to do instead is I'm going to parameterize my curve r of t and multiply and take this r of t that I've now constructed for my curve c and evaluate it at my function value for x and y. So what am I saying here? The goal here, more formally, is we can exchange this then. So let's say I have r of t for my curve. Okay, this is my curve c. Curve c. And I tell you, I'm between two time intervals, right? I'm between a and b. Right? My time here is between a and b. Line segments are usually from 0 to 1. You know, for circles, they would maybe be between some form of pi or something like that. And what we can do is I can exchange this now to evaluate this and change this to a time interval from a to b. And what I'm going to do is I'm going to replace every single part where I see x, I'm going to do it with x of t. As a reminder, what x of t is? That's the x component of my parameterization. And then I'm going to replace this with y of t. And then, where y over say y, my function values. Lastly, I have to multiply ds here. I have to change it with the magnitude of r prime of t dt. Another way you could write that would be the square root of x prime squared of t squared plus y prime of t squared dt. And this is a way to evaluate your integral. So we replace x with x of t, y with y of t. We solve for the norm of r prime of t. A more concise way to write this, and a way that you will see it written many, many more times, and something that's a little bit more formal, is what we, and something that doesn't depend on dimension even, is just saying that I'm evaluating f at my parameterization r of t, and multiplying it by the magnitude of r prime of t, dt. This is usually how you'll see it, and this is usually maybe how you start to think about it a little bit more. All I'm doing is I'm evaluating my parametrization at each one of the points. So wherever I say x, I plug in x of t. Wherever I say y, y of t. If I had z, z of t. This works for multiple dimensions now. So how do I go about now solving this problem? Okay, so in order to solve this problem, we're going to do two things. We're going to split this up. I'm going to split this up right here. And I'm going to write the procedure over here, how we kind of go about it. Because it's the same exact procedure every single time, which is really nice. So let me kind of explain. What do we need to do, right? Kind of think about what we need to do. The first thing you would probably need to do, right, is parameterize your curve C. Parameterize C. And make it R of t, where t runs from A to B, right? I need something like that. I need to parameterize my curve. So let's do this here. So let's have as a reminder what this curve is. It's the right half of the circle. So I'm in step 1 here. So I note that my curve here, it's a right half of the circle of radius 4. So it's just this part. Now, I want you to think about this pretty quickly. Does it matter which direction I'm going in? Does it matter if I go in this direction or this direction? Because that's an important thing. Parameterizations give me a direction, right? I'm going in a certain direction. But doesn't that matter? The answer is no. And why is that? Because think about it this way. What actually physically is this quantity? It is the area made from the curtain above this line. So regardless if I'm going this direction or this direction, the function is still going to be the same at every single one of those points. So it actually does not matter for this type of line integral of a scalar function. Does not matter if I go in either direction. I can go in any direction. The curve matters, yes, but the direction of the curve does not matter. We usually write this, and an important little note here. We usually denote this as, we have this interesting way to write this as f of xy ds in my negative c, so going in the exact opposite direction, is the same as going in the direction. This negative c means I'm going in the opposite orientation. So these are exactly the same for this, for ds here. Because ds you could think about, it's an important thing, ds is an arc length. So the arc length is kind of an absolute value in some way, right? It doesn't matter if I'm going this way or this way, the same arc length. So how do I parameterize a circle? I'm going to be going in the counterclockwise direction. Let's assume I'm going in this direction here. And what I want to do is I want to go from here to here. So I'm going to just write my parameterization down as I know how to do it. I know this is going to be r cosine theta, r sine theta, right? I can use just polar coordinates to parameterize this. If I use polar coordinates to parameterize this, I have a constant radius, right? And the only thing that's changing is my theta. So I can change my theta. So it'll be 4, my radius of the circle is 4, cosine of t, 4 sine of t. And now what's my domain between? Well, you might say to yourself, okay, this is pi over 2, and this is 3 pi over 2, but I need to be moving in the same exact theta direction. I need to be moving always in the clockwise direction. So what I would suggest doing would be maybe thinking about this as negative pi over 2, and this be pi over 2. Okay, so I've now done my first part. I have a parameterization on my curve C. I am now getting ready to go ahead and try to solve this integral out. This is again computing the area of the curtain above this line. So now, over here, the next step, kind of think about what the next step would be. The next step would be probably to compute the norm of r prime of t, right? I'm going to need that. So that's the next step usually. So the next step here is compute this guy. Compute that. And so let's do that here. R prime of t is not too bad. It's negative 4 sine of t, 4 cosine of t. And if I take the magnitude of this, I hope you'd agree, this just becomes the square root of 16 sine squared of t plus 16 cosine squared of t. And what's beautiful about this is that if I factor out a 16, I'll just get sine squared plus cosine squared, which is 1. So this entire thing inside of here is just 16. Therefore, the square root of that is 4. Nice. So the magnitude here might not always come out nice. This is just really good because we have a constant velocity when I turn around a circle. But it's just an important idea when I'm going through it that, if I have something like this, sometimes the magnitude might be really easy to evaluate. Maybe it's not easy at all. But maybe you'll have to use some trick then when I integrate. The next thing I want to do is actually evaluate f of r of t. So plug in wherever you see x of t, or wherever I see y, I plug in y of t. So evaluate f at r of t. So this is the idea of I plug in x at x of t and y at y of t. So in doing this, I'm going to zoom out a tad so we can kind of see all this, the whole picture in total. So I apologize. What I'm going to do now is I have my part 3 here, which f of r of t here, well, f of xy is x times y. So all I'm going to do is I'm going to do 4 times cosine of t times 4 of sine of t. Something like that. And so here, what this does then is this can get written as 16 cosine of t sine of t. This is more complicated, but I would do the more complicated thing, right? Maybe it's xy squared. This would be 4 times cosine of t times 4 times sine of t squared, right? That quantity squared. And so now we have this. And lastly, I know this is a really long part, but sometimes it's a little bit more. Just evaluate the integral now. So evaluate, a to b, f of r of t, magnitude of r prime of t, dt. And so let us do that right now. 4 here would be the integral of xy ds over my curve c can now be written in my parametrization as negative pi over 2 to pi over 2. F of r of t is this quantity right here, 16 times cosine of t times sine of t, multiplied by r prime of t dt. In this case, this would be 4 dt. And this is now an integral. And now it just behooves me now to just evaluate this integral. So let's do it. To solve this, I will need to do a u sub. So u would be equal to sine of t. Du would be cosine of t dt. So you'd get something like 64, right? 16 times 4, integral of u du, or 64 divided by 2 u squared, or 32 times sine squared of t, evaluated between negative pi over 2 to pi over 2. And what's interesting here, if I evaluate this now, so it comes 32. Well, sine squared of pi over 2 is equal to sine squared of negative pi over 2. So this entire thing just becomes 0. And so my answer is 0. So what does that physically mean? Is that okay at 0? The answer is yes, right? Because it's a net area here. So that means the amount that is below my x-axis, this curtain, right? This curtain has been made, right? At every single one of these points, I calculate the function value. And so every single point, I'm kind of thinking about the amount of curtain above the xy axis is the same as the amount of curtain below the xy axis. And so therefore, this integral is 0. And this is the same procedure every single time you do one of these problems. And what's nice is this procedure kind of goes throughout the entire thing, keeps working in different ways. We will see problems down the line where this becomes really, really difficult. And so we might need to use different techniques. But this is always the fail-safe way to do it if you have to do it. And then if you need to use Mathematica or something, you can go ahead. But this is the exact process you would do if absolutely necessary. That's kind of how you do this. And it's a nice little way. So again, parameterize your curve C. Remind yourself, how do I do circles? A big part too is reminding ourselves that this ds here, it doesn't matter which direction. So that's a big one, right? It doesn't matter which direction. Now, the next one is to kind of think about, okay, I need to then parameterize a curve, calculate r prime of t and the magnitude of it, and then plug in your r of t into my function f, and then lastly, evaluate the integral as you do. And you can get 0. It's okay to get 0. It's okay to get negative numbers. All right, let's continue then. You know, what I'm going to do now is you're going to say, okay, well, I'm going to keep doing line integrals of functions here. Line integrals of just scalar functions before we get into vector fields. And line integrals of scalar functions, you might say to yourself, well, what if I don't want to integrate with respect to s? What if I want to integrate with respect to x or y or something like that? You can do, which is really nice. So for instance, if I ask the question, let me actually change this a little bit. If I ask the question, you know, the integral, the integral of f of x, y over my curve C now, but not with respect to s, how about with respect to x? What if I say I want to just move in the x direction? Not even in the x direction, just that I kind of, what I'm doing is I'm kind of just picking points in my x direction here. And I'm trying to figure out if I just move in the x direction and partition my entire curve in the x direction, you know, what will that be? What will the area of this curve be? And what I'm kind of seeing there is what's kind of happening there, that's kind of visualizing this, is I can take this curve here and I can partition this curve by its x values at every single point. And at every single point here. And you can see I'm kind of also sometimes coming back and looping on it again. And if I move in the x direction like this, dx, if I just move in the x direction like this, it's actually giving me a different answer. It's kind of an area too. It's kind of difficult to explain, at least just with x here. But we can actually start to think about something with this once we get to vector fields in a little bit. We can still evaluate something like this with respect to x. In this case, we kind of remind ourselves that, okay, well, let's say x is equal to x of t. If x is equal to x of t, if I parameterize my curve C again, and I want to evaluate this in terms of my curve, this does not mean, again, you cannot just go ahead and evaluate this and integrate this with respect to x. That doesn't make any sense, actually. What this is saying is I'm moving in the direction of x, the positive direction of x. I'm partitioning in the direction of x. And so if I take the derivative of both sides, I hope you'd agree this is just what that would be, right? dx dt is just equal to x prime of t. If I multiply both sides, we see that to exchange this and to replace x and y with my parametrization, I would just need to replace this by multiplying it by x prime of t dt, not the full y of t in this case, because I'm only parameterizing with respect to, I'm only integrating with respect to x here in the x direction, not the y direction. And so if I wanted to, I could evaluate this between 0 a to b. I would again, plug in both of these, f of x of t and y of t. In this case, I would do that again, right? Wherever I parameterize with respect to x, I would do that with respect to y. And then I multiply it by the derivative of that with respect to x. So, I mean, if your equation here, if I wanted to do the same exact thing up here, right? How would I go about doing this problem in this way with respect to x? Well, all I need here, this function is still the same. That's not changing. The only thing that's changing now is when I'm multiplying by. It's not going to be this 4. I take the derivative of 4 cosine of t with respect to x. Well, I mean, just take this derivative, which is negative 4 sine of t. And this negative 4 sine of t would be multiplied by that now, instead of this 4 with respect to x here. And we just evaluate that again. We're going to get a non-zero answer this time, I think. Yeah, we definitely will. So that's what happens. You just take, instead of this magnitude, you don't take that anymore. You just take literally the component x prime. In a similar way, you can probably guess, if I have a dy here and I want to partition in the y direction, I would again change this the same exact way. It'd be y prime of t dt here. And again, what I would do in this problem, right, I was to take y prime of t, which is 4 times cosine of t, and plug it down back here too, and go from there. Yeah, so these two are different ways that you are allowed to take derivatives with respect to x and with respect to y. We're allowed to take these line integrals in a different way. They reflect some form of an area and some form of a something we'll call a work integral in a little bit. But that's at least the basic idea of how to do these problems. So yeah, I hope this makes sense here. I'm going to at least stop here for this video, and in the next video, I'm going to start to tackle, you know, functions and how do we do work integrals and vector fields and all that. But I just want to at least get part here. So kind of going backwards, this first part of line integrals over scalar functions, we talked about vector fields, how to evaluate them, how to look at them, what the idea of a conservative vector field is. Then what we saw is what this line integral now means. What does this line integral actually physically mean, right? It means that I'm just taking an integral over a curve now. It's now a net area. And this we're integrated with respect to arc length. We now see this procedure where I parameterize my curve C. I find the magnitude of that. I then evaluate the function that I'm evaluating on my curve, basically everywhere on my curve over time. And then I evaluate the integral where I do f of r of t multiplied by the magnitude of r prime of t. And we saw two different ways that we could also do this with respect to x and with respect to y too. And we can just multiply y prime or x prime respectively. That's the ideas here. My next video will cover work integrals. How do we do the integrals over a vector field specifically? And then we can start to talk about, you know, how do we evaluate those integrals in different ways. So that's kind of this video here. I hope you guys are doing well. Hope you're staying safe. And let me know if you have any other questions or anything else you want me to do. Have a great one, guys.